Gauss Law, and in particular, it's very useful and powerful to actually derive electric field for things with symmetry, right? With symmetrical symmetry, we found that if we have a line charge density, lambda, so lambda this is in coulomb per meter. Okay, then the electric field anywhere is only radial, and it's given by lambda over 2 pi epsilon naught over r, right? So the field goes as decreases as 1 over r. Okay, and then we also look at things with spherical symmetry. In particular, we did 2 examples, 1 and 2, for uniform charge density rho. So if you have a charge Q uniformly distributed across the sphere, right? So not just on the shell, everywhere, right? Rho here is just the charge divided by 4 pi over 3 AQ. Okay, then the electric field inside is linear in R, right? And the electric field outside, by the way, the electric field is only radial in this case. Outside is given by 1 over r squared. Okay. We also talk about thin spherical shell of radius A. So the charge is only distributed on the surface of the shell, right? So there is a sigma. Sigma is a surface charge density, right? And it's given by Q over the area of the sphere, and the area of the sphere is 4 pi a squared, right? And in this case here, just by solving Gauss's law, we found last Friday that the electric field is 0 inside, right? So if I draw it as a function of r, this is r, right? The radial component of the electric field, and it's only radial. It's 0 everywhere, right? And suddenly, when r is greater than a, then the electric field goes down. There's a jump here. It's just the electric field goes down as 1 over r squared. Okay? And the value of the electric field here at the surface E is given by sigma over epsilon. Okay, pointing radial. Right? Just if I can get this formula here, just plugging in sigma will be equal to Q over 4 pi a squared. I get this formula at r equal to a, then the a squared cancel r squared. Right? You left with sigma over epsilon. So that's the value of the electric field right over here. And then it just drops as 1 over r squared. Okay? We also look at I don't know what we call this symmetry, I guess mirror symmetry, right? If I have an infinite sheet, right? This is the C direction, right? And there is a surface charge density, sigma, okay? Then applying Gauss law here, we found that the electric field, first of all, the electric field has to be normal, right? It's only normal. If you're not familiar with this argument about symmetry, you can ask me maybe after class or always hour or maybe discussion, we can go through it again, right? But we did this, I mean, it's kind of subtle, but we did it already last week, and we found it has to be normal, and applying Gauss law gives you En has to be equal to, in this case, remember, sigma over 2 epsilon. Okay? So it's sigma over 2 epsilon naught here, pointing in that direction, and sigma over 2 epsilon naught pointing in this direction. Okay? So if I plot just like here, if I plot the graph of the value of the electric field as a function of z, right? And it's just normal. So it's over here is sigma over 2f gamma. And over here is minus direction is minus sigma over 2f gamma. Okay? Because the electric field is pointing in the negative direction. Okay? So things doesn't have to have in this problem of an infinite sheet, nothing has a zero thickness, right? In reality, things always have a finite thickness. We can also solve this problem for a finite thickness problem. So suppose I have an infinite slab. Of thickness. Okay. Fine. Let's just make it simple. Let's make it 2D, right? What is the electric field? Everywhere. Right? So, any guesses? By the way, any questions so far? Everything is clear? Right? Should be pretty straightforward. Right? So, let's define our coordinate system. Let's call that C. And C equal to 0 is exactly in the middle of the slab, right? So the electric field, same argument of symmetry, right? The electric field has to be normal. The electric field is only pointing in the C direction. Okay? And for C greater than A, right? Or C less than A, applying Gauss Law, you'll get like the following. This is A, and this is minus A. Right? Then the electric field here is sigma over 2f naught. And the electric field here is minus sigma over 2f. Okay? How about in between? What does it look like? We'll solve it, but it has to be a little bit, right? By symmetry, right? If things looks like this, is that right? Then it's, that the argument of symmetry doesn't work. But anyway, I don't want to argue this on symmetry on this. But let's solve it. Because it will be very illuminating for other problems that you want to look into, especially with conductors. So how do we solve this problem in this region? Again, same thing, right? You apply a Gaussian field. This Gaussian field is very, very powerful. Right? You apply a Gaussian field. It can be finite thickness, it can be differential thickness, but in this case it's finite thickness. If I look at that field of thickness 2c, so this is c minus c, right? Okay. Then Gauss's law says that the integral, because the electric field is only in the c direction, right? The flux is just E in the c direction times A, right? Electric field pointing in that direction, normal is in that direction. And over here, E is pointing in this direction, asymmetry, and is in that direction. So you have a factor of 2 here. Right? And the whole thing has to be equal to, remember Gauss's law? 1 over epsilon naught, right? And so all the charges inside, right? Oh, by the way, I forgot to, this has a charge density. Okay? Go everywhere along the slab. Uniform. Right? So this becomes just rho times A times 2CA. like this, you get Z, that A cancel, that 2 cancel, right? The rho Z, right? Okay. Did I make a mistake somewhere? No. Except that I need to make a connection between. So as you see, it's linear, right? That's a lesson. Okay. The electric field is linear.
Why is the charge constant as you move away from the sheet?
Why is the charge? I cannot see.
Like if you go away from the sheet, why does the charge stay constant as you go like that?
In the field. The field.
Yeah.
Because this is infinite, right? So it doesn't matter whether you here or you here. Things look the same, right? You see my point? No.
Because I mean, like
Meaning that there is a, if this goes, if this, there are two arguments, right? First argument, if this is infinite, it doesn't really matter where you are. Things always look the same, right?
oh,
And another argument is that Coulomb's law, electric field goes as a, that's a very good question, by the way. Coulomb's law, electric field goes as 1 over r squared, right? For point charges, right? So for a point over here in C, right? All the charges that matter, that gives rise to a significant electric field at that point, right? Has a scale of C also, right? So the charge here, the charge in this circle, inside this circle, is sigma C squared. But the field goes down as 1 over C squared also, right? And the C squared cancel.
oh,
You see, right? Okay. The two ways to look at this. One is just by symmetry, right? If this goes to infinity, right? It doesn't matter whether you're here or you're over there. Things look the same.
So would that be why the infinite line charge wouldn't give you the same result? Because if you look at it from the point of view of anywhere you are, it still looks like a line that's
Yeah, but the
line is.
it's not exactly the same, right? Because if we cross here, I don't know how to add it. I said, good point. There's a subtlety there.
No, it's because the line of charge only has a single factor of r, not two factors.
Yes, if you the second argument tells you the second argument. The first argument there's some subtlety that we can talk after class, right? But the second, if I use the second argument, right, at some distance z, right, all the charges that give rise to a significant component in the electric field has to come from some scale like that, right? Everything else beyond, it's much smaller, right? So the electric field goes as 1 over c squared, right? From Coulomb's law, right? But the amount of charges in this segment of length z, right, goes as lambda c. Right? Only things that are in this segment of line segment of C matter, right? Everything else is almost this give you a diminishing contribution, right? So the C cancel one factor of C, so the electric field goes as 1 over C, or 1 over R, right? Yes. So that's why you have that contribution, right? But for an infinite slab, it's a sigma C squared, it cancels the C squared in the denominator, so it's constant. Mm-hmm. Good question. Good question. Okay. So the only thing left, where was I? So if I have a finite thickness slab that's infinite, right? Then this thing is linear. It goes like that. And I need to convince you, but you can do the calculation yourself, that there is no discontinuity there, right? Because sigma, I hope I'm not missing a factor of 2 somewhere. I like to do that sometimes. But sigma is just, how do you make the relation between charge density and surface charge density in this case? Sigma times 2a, no, rho times 2a is equal to sigma, right? Is that clear? Right? If I want to look at the surface charge density, right, then I just have to multiply the volume charge density times the thickness. Right? And if I do that, multiplied by 2a, right? Then I get this. This is did I make a mistake somewhere? No, you got it right. Right? Then the 2 cancel. I'm left with a sigma a over epsilon naught. Okay. This is just algebra. You can do it at home, right? The lesson to remember is for the infinite slab, the electric field goes linearly inside, just like in a spherical symmetry, right? In a spherical symmetry with a uniform charge density, right? The electric field inside is linear. Outside, it drops as 1 over r squared, right? In this case here, it's linear inside the slab. It's flat outside. Okay. Question?
Oh.
Clear?
Why did you multiply the density times the?
Oh, if I want to, this is the volume density, right? Rho is the volume density.
Yeah.
Charge density. Right? I want to make a connection between volume density and surface charge density, or area charge density in this case, not surface. There's no surface here, right? Because this is infinite. This is finite thickness.
Yeah.
Right? So if I consider, say, if I just consider a block like that, right? Has a, if I look at it, it has a, suppose I make a big Gaussian pin box here, right? This has a density rho and has an area A, right? And I want to look at the amount of charge per unit area, right? And I call that sigma, right? Then it's just sigma times A is just the total charge inside, right? Right? Then it has to be equal to rho times A times 2 rho times A times 2A. I'm using A. But this area, right? Area, right? And 2A is the thickness of the slab, right? The A cancels. I'm left with sigma is equal to rho times 2A. Okay? Is this clear? I see some confusion. The amount of charge in this Gaussian field is the same, right? It's Q, right? You do it 2 ways. One is by the total charge is just the volume density times the volume, right? Which is what I did here, right? But I can also consider an area density, right? So in that case, the total charge is just an area density times the area of the field, right?
So what do you do sigma rho over 2a?
Sigma, that's what it is, right?
Under?
Oh,
At the
rho
bottom?
times 2a. This is not a function, by the way.
Yeah.
Rho times 2a is equal to sigma. So sigma is. Did I make a mistake?
And you wrote it right over
This
here,
thing
so.
This thing that you taught it. I wanted to write rho is equal to rho is equal to sigma over 2k rho I minus prime.
Okay.
Okay. So everything is consistent. At the
Yeah,
end of the
yeah.
day, you should find this, right? I might make a factor of a mistake. I don't. But I didn't. But electric field looks like that in this lab. Okay. Any questions so far? Okay. So, what can we see? So, one more example. I'm not going to do it, but you should try to do this at home. How about if I have a big spherical shell? Radius A and B, right? I'll tell you what A and B. So this is actually a spherical shell in BD, and this is radius A, and this is radius B, right? And there is a density rho in there, right? And rho is just uniform, by the way. Uniform density. And rho is just Q, whatever charge I put in there, divided by the volume, right? And the volume is 4 pi over 3 V cubed minus A cubed, right? Okay. Find the electric field everywhere. Right? Same argument, that the left-hand side of the Gauss law is the same, right? Because this has a radial symmetry. So the electric field looks like that. It has to be radial, R, right? G, A, okay? Now, same application of Gauss law, no charges inside, right? So the electric field is 0 here. Okay. And outside, this line here, that goes as 1 over r squared, right? In fact, it's just Q, right? Q is just the density times the volume of that big shell, right? This is just rho times 4 pi over 3 V cubed minus A cubed, right? Over r squared. 4 pi epsilon naught. Right? So what happened here? Is it a straight line? That's what I want you to solve at home. How many of you think it's a straight line? How many think it's not? Wait, did you raise your hand twice?
No, I didn't think so.
Okay, so you think it's not, right?
Yeah.
How about you? Ramsey? It's straight.
I think it's not.
It's not. Oh, the choosing. It's not, right? Yes. The answer is it's not. Right? Why?
Because it's a bunch of thin spherical shells.
Sorry?
Because it's just a bunch of thin spherical shells and that's not linear.
Oh, but outside it's it's 0 here. No, you got the point, right? Yes, correct. Because it's a bunch of that, right? And when you sum them up, it's not linear. That's one way to see it, but there's a somewhat more transparent way of seeing it. You can think of this as remember, electric field satisfy principle of superposition, right? Okay. So if I look at you have a right kind of a so this is hollow, right? the way I think of this is just a sum of the positive uniform charge density of radius B, right? Okay, plus remember the fun thing about electricity as to compared to gravity, there's two kind of charges, right? Gravity, everything is attractive. But for electricity, electrostatic, you have two kind of charges. So you can either repel or attract, right? So you can play games, and also both satisfy principle of superposition, which is what you said, right? So you can play games to solve the problem. In this case here, this shell here is just the sum of that plus, say, minus charge, uniform minus charge, so a sphere of radius A. Right? The sum of these two become that. Right? Okay? And the field, for this part, the field, we solved this already, right? The field is what? The field is in all the way to B. Right? Okay. And here, what is this field? It's so it's between, I'm not so interested in the field. The field, yeah, you're right. Here is it's like this, right? One. It's minus R, right? But what matters is between A and B. Okay? That's what we want to solve right now. Right? In fact, this contribution here cancels that contribution. That's why we have 0. A transaction from 0 to A. Right? But over here, from A to B, right, it's already outside of this sphere. So this goes as 1 over R squared minus 1 over R squared. Okay? So the contribution between A and B has two components. One of them is linear. This part is this part here, and then you add that one, right, with the same density. Okay. So you get something more like, so this is wrong, right? So what is the, how does the curve look like? Is it like this? Or is it like this?
Let me take this second.
This one? How many of you think is that? How many of you think is this? What's the best way to see this? Actually, I don't know right now. I think it's somebody has a mathematical guy at home, you can plot it.
Well, I'm just thinking that if you're taking the sum of these two graphs,
Yes.
the part from A to B of the -1 is
Right.
you're going to be subtracting a larger amount.
Well, closer to A, you have to subtract a larger amount, right? Closer to B, it's a much smaller amount. Think about this. Think about when B is much larger than A.
Yeah.
Right? Right? So, if B is much larger than A, right, let's draw it here. A, B over there, right? 1 over R squared, right? So, just by the argument of these two, the shell is a sum of these two spheres, right? Then you can if this is true, you can pretty much neglect that, right? You can neglect the small sphere, the negative sphere, right? So it has to look pretty linear. In that case, then it is linear, right? If you can ignore the second sphere, right? But you can't. Close to A, you cannot, right? So over here is linear, right? But over here, it has more of the component that comes from 1 over r squared, right? So things will look like this.
Also, I think it can't be 1 because if you draw a straight line connecting the endpoints from A to B, then like 1 would imply that you're somehow going over that, and that it should decrease.
Say it again.
Like because 1 is concave down, then if you draw a straight line, which is just a contribution from the positive 1,
Yes.
then like
Correct, because if it's like this, right?
yeah.
But this, the contribution from the second sphere is actually negative, right?
Yeah.
Yes. That's also a very good argument. In fact, maybe both of them, right? Illuminate on this problem here, right? So if we ignore the second sphere, it has to be straight, right? And the contribution coming from the second sphere is negative, right? So you have to subtract, right? You cannot add.
Wait, no, the contribution from this solid sphere isn't from 0 at A, it's a little higher up.
Yeah.
Yeah.
So the straight line can start at 0.
Yeah.
No, they should start at 0 because they exactly cancel
But
from
it's the
0
same
to A.
thing, right?
But if you're talking about removing the negative and just looking at the
This is,
graph.
I'm just looking at this. This is the contribution from this part here, from A to B. I like this. This is an interesting discussion. I get you involved.
Well, no, I agree that 2 is true, but I think that the argument that he's making is wrong.
Oh,
Because,
okay.
if you're going from the assumption that the line is going to look a certain way, if you're ignoring the negative, then you're going to be going from 0, 0 to B something. Not from A 0 or something, right?
Yes.
So you're going to have a higher value at A.
No. I see your point. Let's do this again, right? The answer is correct. The answer is this, right?
Yeah, it is 2.
Right. But the argument from Nicholas is that if it goes like this, right?
No,
Yes.
because from 0 to A,
Uh-huh.
the positive and the negative ones exactly cancel because they're the same charge density, right?
Yes,
So
yes.
then from 0 to A, it should be 0. But then if,
Right,
you,
right.
if you just consider from A to B using
Right.
only the positive contribution,
Right.
then you're saying.
But I think there is some subtlety here because Calvin is saying that if you want to do it that way, right, this actually the contribution from the sphere,
okay.
right, has to go like that, right, not like this. That's effectively what he's saying, right? So, just
Okay, I see.
when you make your argument, you have to be a bit more careful. Right? But at the end of the day, this is true, right? Okay. So this is actually just an aside because I want to talk about something else more important here. Okay. So make sure you do this at home, right? Solve it for big spherical shell, right? Do it, mathematically correct. Just don't make argument. You can just solve the algebra. But let's go back to our example of the spherical shell. Okay. Of radius A. Okay. Then the electric field at A is given by, where was that? At the surface, right? Good thing I haven't erased this, right? There's a thin spherical shell. The electric field right outside, right, for A plus is just sigma over epsilon naught. There you go. Okay? And the electric field inside, let's see. Okay?
Can you say what is E of A plus?
Oh, this is just slightly outside of the sphere. Okay? Maybe it's a bad definition. I'm just saying this is for R is equal to A plus some small number. Yeah? And this is at R equal to A minus some small number.
What if it's exactly A?
Now, that's a question, right? What is it when it's exactly A?
Yeah.
But this is mathematical idealization, right? In reality, physically, things has finite thickness. So that's part of the reason I went through this discussion, right? It's not for, because otherwise it's just homework, right? Remember, for an infinite slab, you get something that's linear, right? Right? And for a big slab, for a big spherical shell, that's a very good question. You get something that's, now that we decided that it's this way, right? Okay? So, in reality, there is nothing with zero thickness. Right? Things are always a shell of some differential thickness in this case. Right? So the electric field, this is A, right? And some thickness epsilon, say, right? So outside, we have 1 over r squared, and here is sigma over epsilon, right? Okay, and 0 here. Okay, so what you have is something that looks like that. It's not linear. Right?
Yeah, it just is.
Basically, it's this graph here, except that you squeeze A and B together. Okay? Questions so far? Yes.
Okay, might be that like that. So it might be the number 2 graph.
You like 2 graph? Yeah, this is number 2.
Or the number 1.
Oh, you think it's number 1? Okay, well, I think at the beginning I did a poll, half said number 1, half said this, the other half says that. And I think between Nicholas and Darwin, we agreed that it's actually this, right? And Julian.
I don't know.
No, earlier, I think your first argument was based on a principle of superposition.
Oh,
It's
yeah,
a
yeah.
big shell,
Yeah.
right? It's just a bunch of shell put together, which is, it's the right kind of approach. And then we realized that it cannot be linear, right? And then we realized that